Hi students, welcome to preliminary chemistry and the water topic. This is video number 21 on calorimetry. In the last video we started to look at the specific heat capacity of water and make a comparison with a few other substances. Now, how do we do that? How do we calculate what the amount of energy required to heat 1 gram of water up by 1 degree is? Well, we use a calorimeter as a device which allows us to measure heat energy. And then we can make comparisons on the basis of dissolving substances in water or of carrying out certain types of chemical reactions in order to make comparisons about their specific heat capacity and what sort of energy is released in each of these processes. We're fortunate in that many reactions that occur do so in an aqueous state. That is, they're dissolved in water, or at least a lot of the components are dissolved in water. And that means because of water's high specific heat capacity, it's a very good substance to use as a medium for the absorption or release of heat energy. This allows us to carry out a number of different experiments, a number of different reactions in order to determine what their energy requirements or implications are. The device that you can see in front of you is a fairly simple calorimeter. In here is the reaction mixture. We usually make sure that there's some level of insulation, so you can see these are polystyrene cups. So the point with these will be that they are insulators. They will try and keep all of the energy within the system, so none radiates out and also none is brought in from the outside. Obviously, we need some device for recording the change in temperature, so a thermometer is the easiest thing to do there, and then perhaps any sort of agitator or stirrer that may also help to ensure that the heat is equally distributed and that our thermometer is measuring all of the temperature changes. What this allows us to do is to use what's often referred to as the MCAT formula. So delta H is equal to minus MC delta T. And this is used to calculate the enthalpy change. That is the change in the energy state before and after the reaction. What we do with this is we look at the mass, which in this case would be the mass of water. So that's the I'll call it solution because there may well be something in there, and I'll put water in brackets. C is the specific heat, and the specific heat capacity is going to relate to this substance, so either water or the solution that's being heated, and the delta H is equal to the temperature after the reaction minus the temperature before. Okay, so that's just equal to the change in temperature. Now, one thing that's important to note here is that the temperature doesn't always go up, sometimes it goes down. Some reactions will release heat to the surroundings and other reactions will actually absorb heat from the surroundings. So we can use this value of delta H in order to calculate this, and we're going to explore this in a little bit more detail, not just in this topic, but also in future topics. So the way this principle works is that if we can measure the temperature of the water before the reaction and then monitor the reaction and identify the maximum change, often if the water heats up, it will heat to a maximum value and then it'll start to cool again. If it cools, it may cool to a base value and then start to heat up again. So we make sure that we find the maximum change that we can, and then it allows us to classify the reaction as either an endothermic or an exothermic reaction. An endothermic reaction means heat goes in, and therefore the delta H value is positive. Heat is absorbed from surroundings. And so in this case, water. So if heat is absorbed from the water, then the temperature of the water will actually drop. A delta H value, which is negative, and of course a positive value is endothermic, meaning almost literally heat in. Negative is when heat is released to the surroundings. Again, in this case, often water, and this is going to be an exothermic reaction. So if heat is released into the water, then that means the temperature of the water will rise. The problem with calorimetry is there are three very important assumptions, and if any of these assumptions is incorrect, then we can introduce error into our values. The first assumption is that no energy absorbed or radiated by the calorimeter is either coming from, that no energy is absorbed from outside to within. So what we're trying to do here is maintain, this is kind of a bit of a poorly worded thing. I'm going to have to just jiggle around with this a little bit. The assumption here is that all of the energy change has been absorbed by the water. So the container itself isn't actually taking in any of the energy or putting any energy in. So that if, for example, the temperature were to rise, but some of that temperature went to heating the container of the calorimeter, then that would not be heating the water, and therefore the value of that temperature rise would be lower. I don't know if that makes sense, but we'll have a little bit more of a look at that because this is kind of like what is going on. The second is that there isn't any energy exchange external to the calorimeter. That is, the calorimeter itself and maybe the air outside it, wherever it happens to be sitting in, is not occurring. We haven't put the calorimeter in direct sunlight, for example, and that's heating up because of the external. So we don't want, assumption one is the calorimeter itself. We don't want it to be involved. Assumption two is no surroundings are going to affect it either. So only what's happening within the calorimeter is going to affect the results, and anything that doesn't fit with that assumption is going to affect our accuracy. And the final one is that we are assuming that the specific heat capacity of the solution is the same as that for pure water. And as I looked at before, this value of 4.2 joules per Kelvin per gram only works for water. If the solution is not exactly 4.18 or 4.2, then again, we're going to introduce an error into our calculations. And for most practical purposes, all three of these assumptions are reasonable assumptions to make. And certainly in terms of the experiments that you'll do in class or in your school laboratories, you'll find that there will definitely be errors present, but we can still do our calculations and make comparisons with theoretical values in order to get an idea, at least, of how this process works. We'll look at how we use the delta H calculation value in the next video. Thanks for watching.